Module 18, Closing. The learning objectives for this module are to identify factors that affect loading partitions, explain the hydraulic gradients associated with the internal erosion processes, recognize scenarios where probabilities must be combined for a single failure mode, and adjust event tree probabilities for dam or levee modifications. This presentation covers a variety of topics, including loading partitions, a review of hydraulic gradients for the internal erosion processes, and assessing modifications. Loading partitions. Flood and earthquake loading partitions must be carefully considered and discussed as a team. The partitions must capture where changes in performance are expected, in other words, inflection points in the system response curve. It is important to note that partitions can vary from failure mode to failure mode, and even from node to node for a given failure mode. Different loading partitions may be considered for each component of the risk equation: hazard or loading, performance or potential failure modes, and consequences. The selection of the loading partitions directly affects any supporting analyses to be performed and the subjective probability estimates during a team elicitation. Several factors to consider when selecting loading partitions are shown on this slide. Always evaluate performance up to the embankment crest, even if the probable maximum flood is at a lower elevation. Other potential inflection points include major changes in the foundation profile, changes in the embankment cross-section, past performance thresholds, record stage, top of active storage, etc. The top figure is an example of a design change with the embankment cross-section that occurs at 1 in 1000 AEP with a partial height impervious core and chimney filter. Flow-through rock fill can occur above the impervious core. The bottom figure is an example of a design change that occurs at 1 in 50 AEP with a partial height chimney filter. Many USACE filters were designed for slope stability considerations, not defensive measures against cracking in the upper part of the embankment. As a result, an unfiltered exit exists above this elevation. As with any node in an event tree, provide the rationale for each loading partition to provide a clear understanding of its significance. The first table is an example of concise rationales for reservoir pool partitioning. If tailwater significantly influences performance, provide its rationale in a similar format as shown in the bottom table. As illustrated by these example curves, the conditional probability of failure could have a wide range of shapes. For a good levee, the probability of failure may remain low and reliability remain high until floodwater elevation is rather high. In contrast, a poor levee may experience greatly reduced reliability when subjected to even a small flood head. The actual curve may be closer to an S-shape or intermediate curve, which is similar in shape to the good case for small floods, but reverses to approach the poor case for floods of significant height. A straight line function is also shown, representing a linear relation between reliability and flood height. Linearity would not be expected to be the general case. After estimating all probabilities for the event tree, plot the system response curve and review its shape to confirm it makes sense and is consistent with the team's understanding of the estimated performance. Can inflection points and abrupt changes be explained? Are additional points needed to provide better resolution? The following examples illustrate these points. In this example, the system response probability remains constant with increasing stage. For example, it reaches a probability of 1, or the tailwater rises, reducing gradient such that the probability can no longer rise. In this example, the system response probability abruptly increases and then continues on the same initial trend. Is there a physical explanation for increasing the system response probability by an order of magnitude at pool of record, for example. This example cannot happen. Probabilities must be monotonically increasing in general. This is an example of a brittle system with a threshold stage where performance changes dramatically. Are sufficient points defined over small but critical ranges of stages. In this example, tailwater reduces gradient. Since stage has already passed through a higher system response probability at lower stage, timing and rate of progression are important. If progression is fast and tailwater rises slow, the system response probability may not come down as much or at all. In this last example, are sufficient stages evaluated to identify inflection points? Hydraulic gradients. As we have seen in this training course, the hydraulic gradient influences the likelihood of initiation and in some cases progression of each of the 5 internal erosion processes. For concentrated leak erosion, it is used to estimate hydraulic shear stress for initiation. For backward erosion piping, it includes vertical exit gradient for initiation and horizontal gradient for progression. For suffusion, it includes exit gradient for initiation. For soil contact erosion, it is used to estimate Darcy velocity for initiation. For internal migration, a vertical downward gradient is required. Direct use of critical velocities or gradients determined from laboratory experiments is limited by the narrow range of materials tested and an apparent significant scale effect. For backward erosion piping, initiation is governed by Terzaghis classical equation for critical vertical gradient, whereas the average gradient informs the hydraulic condition for progression. For scour, you cannot just discuss hydraulic gradient. For concentrated leak erosion, hydraulic shear stress is a function of hydraulic gradient as well as pipe or crack geometry, and the critical shear stress is dependent on erodibility. For soil contact erosion, the Darcy velocity is a function of hydraulic gradient and horizontal permeability, and the critical velocity is based on a theoretical critical value from experiments, which is a function of particle size and porosity. Lee and Fannin in 2021 developed relationships for critical hydraulic gradient in one-dimensional vertical seepage, as shown on this slide. For internal migration, a downward gradient is needed to move eroded particles into the open defect. There also needs to be enough seepage gradient in the defect to transport eroded particles to the exit. The flow path length for hydraulic gradient calculations can vary with embankment cross-section. This slide provides examples of multiple flow paths to be considered for concentrated leak erosion through an embankment based on design changes in the cross-section. At the top left, this dam has a thin, partial height impervious core with pervious shells. Flow path A above the core could be backward erosion piping, where the roadway acts as a roof, or seepage-induced sloughing of the downstream face. Flow path B is concentrated leak erosion through the core, but the pervious shell may or may not provide a filtered exit. In addition, if the pervious shell has excessive fines, common cause cracking may occur, resulting in an unfiltered exit at the downstream face. At the bottom left, this is a homogeneous dam with a partial height inclined chimney filter. Flow path A is above the elevation of the filter and has an unfiltered exit for concentrated leak erosion at the downstream face. Flow path B has a filtered exit at the inclined chimney filter. At the top right, this dam has 3 design changes that must be considered. Flow path A has an unfiltered exit for concentrated leak erosion at the downstream face. Flow path B is concentrated leak erosion through the thin impervious core, but the pervious shell may or may not provide a filtered exit. In addition, if the pervious shell has excessive fines, common cause cracking may occur, resulting in an unfiltered exit at the downstream face. Flow path C is concentrated leak erosion through the thin impervious core and has a filtered exit at the inclined chimney filter. Lastly, at the bottom right, this dam has no filters, and the downstream berm lengthens the flow path for concentrated leak erosion. When preparing more and less likely factors, do not use qualitative terms like low gradient. Backward erosion piping can progress with average gradients as low as 0.02 to 0.05 in fine to medium uniform sands. Always specify hydraulic head difference over seepage path length, or H/L. Don't just provide the numerical value of gradient. This assists with quality control reviews and helps to clearly communicate seepage path length. Discuss key assumptions and parameters for estimation of critical gradients. You cannot just discuss gradient for concentrated leak erosion. Hydraulic shear stress is the parameter that drives initiation. It is a function of hydraulic gradient as well as pipe or crack geometry, and the critical shear stress is dependent on erodibility. The top table illustrates how the hydraulic shear stress increases with both increasing hydraulic gradient and pipe diameter for cylindrical pipe. The hydraulic shear stress is then compared to the critical values in the bottom table. For dispersive and other highly erodible soils, concentrated leak erosion may initiate in narrow pipes or cracks. For example, an average gradient of 0.5 in a 2 mm and 5 mm diameter pipe, the hydraulic shear stress is 0.051 psf and 0.128 psf respectively. When compared to the critical values listed, concentrated leak erosion is likely to initiate for highly erodible soils. Assessing modifications. The formulation of structural risk reduction measures to address potential failure modes will focus on one or more nodes of the event tree to reduce the likelihood of their occurrence. These are the nodes that are typically targeted for backward erosion piping. Structural risk reduction measures must either interrupt the continuous flow path, provide a filtered exit, or reduce hydraulic gradients. These are the nodes that are typically targeted for concentrated leak erosion in the embankment. Providing a filter as a defensive measure is the most effective structural risk reduction measure. Modifications to the upstream cross-section can also be performed. To achieve flow limitation, an upstream facing element could be constructed. To provide crack filling action, an upstream cohesionless zone could be provided, but it must work in conjunction with a downstream zone that is filter compatible. These are the nodes that are typically targeted for concentrated leak erosion along the embankment foundation contact with the installation of a cutoff wall. A cutoff wall effectively addresses the continuity of the flaw and introduces the significant benefit of flow limitation if there is a construction defect in the wall. However, the concentrated leak erosion potential failure mode becomes non-credible, and internal migration becomes the potential failure mode. For internal migration, only a downward vertical gradient is needed for initiation. A stable roof is not applicable for stoping, and the breach mechanism becomes sinkhole development. Installation of structural risk reduction measures, like cutoff walls, can also introduce new potential failure modes as the flow regime is changed. This presentation discusses the first three potential failure modes listed here: leaks through seepage barriers, erosion along or through bedrock joints, and erosion of solution void infill. In the left figure, the bending moment of the barrier at the top of rock is higher due to the stiffness contrast between the soil and rock and may cause barrier cracking. At the embankment foundation interface, concentrated seepage pathways are more likely due to a concentration of gravelly soils at the base of the alluvium or differential movement between the embankment soils and rock. Similarly, the coincidence of a crack in the seepage barrier and a seepage pathway may occur where barrier cracking occurs at the interface between rock types with different stiffnesses, where bedrock jointing also often occurs. The middle figure shows hydraulic fracture on the downstream side of a barrier due to elevated water pressures from flow through the defect in the barrier. Hydraulic fracture can also be caused by high water pressures on the upstream side of the barrier and leakage through the defect, stress redistribution in the core during barrier construction, or post-construction deformation. In the right figure, the barrier is constructed through a zone of high conductivity, and a large gradient is imposed on the uncured concrete, which erodes finer particles of the concrete mix before curing, resulting in a segregated concrete backfill. This mechanism can develop where concentrated flow occurs through bedrock joints beneath or at the ends of the barrier. Increased water pressure developed due to the seepage barrier will reduce the effective stress on the joint and has the potential to dilate the joint and initiate seepage pathways through the bedrock that were previously not significant. The increased gradient along the joint also increases the potential for erosion of joint infilling. If the barrier is installed too shallow and continuous open rock defects pass beneath the barrier, collapse of the embankment fill and underlying alluvium can also occur, leading to sinkholes manifesting on the upstream or downstream slopes. In addition to this example of the flow path bypassing the barrier vertically, it is possible that the flow path could bypass the lateral extents of the barrier. References. Here are some overarching references to consider adding to your technical library. Fell et al. 2008, also known as the Piping Toolbox, was a joint effort between the University of New South Wales in Australia, URS Australia, now AECOM, USACE, and Reclamation. It was a seminal document and was significantly updated in 2024 by the University of New South Wales. It can be downloaded for free from their publications website. Fell et al. 2015 is a good overarching textbook that covers investigation, design, risk assessment, and construction. It also contains the Fell et al. 2008 Piping Toolbox in the appendices. USACE was a co-author along with other agency representatives for ICODS for FEMA P1032, which can be downloaded for free from FEMA's publications website. ICOD Bulletin 164 can be downloaded from ICOD's publication website. It is free for USSD members. USSD 2021 is a white paper that presents a brief overview and summary of the topic of internal erosion in dams and their foundations, drawing extensively from other relevant publications, namely the Best Practices Manual. USSD members can download it for free from USSD's publication website. Zhang et al. 2016 is another overarching textbook and can be downloaded by chapter for free if your agency subscribes to Wiley's online library. This concludes this presentation.